Hi, this is a special lecture. In this lecture, we'll be talking about a concept called one pixel attack. It's fascinating. When I first learned about this concept, I was really mind blown. The basic idea is that you can fool a deep learning algorithm, or basically a neural network, to think that when you provide an image of a horse, it can think that the image is actually a frog. And what do you have to do to make neural network behave like a crazy guy? Just change the value of 1 pixel. So have a look at this image. It's that of a horse, and here you can see a black dot. That is the pixel whose color is changed. And just because of that one change, this entire image is predicted with 99.9% confidence that it's a frog. So we'll be discussing about this fascinating concept called one pixel attack in this lecture. So we'll be briefly going through this paper, which was a seminal paper published in this domain for the first time. We'll be discussing how theoretically this is implemented using an algorithm called differential evolution. And we'll also be implementing a one pixel attack code ourselves. So welcome to the lecture. This lecture is part of our course on explainable AI theory, applications, and research. And in one pixel attack, we will learn how modification of just a single pixel, as you can see here, leads to completely different prediction by a neural network. So you might have seen this concept where an image, you can take any image and let's say this looks like a panda, and you can add a very small noise. So in this case, 0.007 times this noise, which is very small, is added onto this image, initial image of panda. And the image looks exactly like panda again after adding the noise. But then the neural network makes a prediction that initially it was 57.7% confident that this was panda. But now neural network says this is 99.3% it's gibbon. The image for us humans, both of these images look exactly the same. The only difference that was done was adding a small imperceivable noise, 0.007% of this noise. And this concept is called adversarial examples. And if we are deliberately creating adversarial examples to fool the neural networks, it's also called as adversarial attacks. This concept has widespread applications in self-driving cars and various other industries, fraud detection, etc., where you can engineer inputs to a neural network, and the neural network can make a prediction which is totally unexpected, right? But then there is a question. In this lecture, we are discussing about one pixel attack, right? So what is it? Why do we care about one pixel attack? In this previous example, we saw that all the pixels, like we are adding a noise kind of image whose size was the same as that of the original panda image, right? So we were kind of modifying all the pixels. But what is one pixel attack? In some cases, when you make modifications to an image, even if you are making modifications to very few number of pixels or a handful of pixels like this. So this original ship image, it's a bit pixelated. It's 32 by 32 pixels. It is added with this noise. You can see that the values of the added pixels are red, green, or blue, or a combination of those. You can see that the resultant images in all these three cases, you can see the added noise or added extra pixels, right? You can perceive it as a human. And this is one example where modifying a large number of pixels or even a handful of pixels sometimes is not very favorable, because you can clearly see that somebody has done some tampering with the input image. But if we take this really to the extreme, where we say, okay, how about this? We modify just 1 pixel. And will that be enough for fooling the neural network? And if we are only changing the value of 1 pixel, it might be very difficult for a human to see and identify that some change has been made, right? That's the basic premise behind this idea of one pixel attack. So we will see more about this in detail. So obviously, this is an extreme case when somebody is designing an adversarial attack. If somebody wants to design a system where a neural network has to be really fooled, You won't be keeping the constraint that, hey, I'll be modifying only one pixel. You could do whatever you want, but this is an extreme case which is very, very interesting, where just one pixel modification can lead to fooling the neural network. So can this happen? If yes, let's see how. So one pixel attack is very different from regular adversarial attacks. In regular adversarial attacks, this image of a pig can be ever slightly modified by 0.005 times this noise. It looks like pig again for us, but neural network says it's an airliner. In one pixel attack, for example, in this image, you can see there is a small dot inside this red circle. That dot is the one pixel that is modified. And because of that, the original image, which was classified as a teapot with 24.99% probability, is now classified as a joystick with 37.39% probability. This is one pixel attack. And if that red circle was not there, I guarantee you would not have realized that that is the modified pixel. I could have given you a clue saying, hey, here is an image. One of the pixels in this image is modified. Find out which one. You probably won't circle that image, that pixel inside the red dot. You may or you may not. But in either way, it's very difficult for a human to say that this picture of the teapot has been modified. Right. So that is the value of one pixel attack. You can you can make a change to that pixel by whatever value the change can be. If the pixel values range from 0 to 255, you can add like as high value as possible so that the image may be completely white, or in the other extreme, the pixel may be completely white. In the other extreme, the pixel may be completely black. But in adversarial attacks, in the regular adversarial attacks where all pixels are modified, there is no constraint about you are modifying only one pixel. You are free to modify any number of pixels, but the amount by which you modify is very much limited. The amount, you put a cap to the amount. So every pixel is very slightly modified. In the one pixel attack case, one pixel, which is selected very carefully, is modified to how much ever possible. There is no constraint on how much you can modify that pixel. That's the difference between a regular adversarial attack and one pixel attack. So this paper, which talked about one pixel attack, published in Archive, I think in 2017, it has almost 2,700 citations now. It's a brilliant paper. I absolutely love. I think this was published in 2019, maybe the revised version. We have to check the date, but basically this paper talks about, rather than constraining the extent by which the pixels can be modified, you constrain the number of pixels you are modifying. You say okay, I can modify only 3 pixels, 5 pixels, or in the bottommost extreme, I can modify only 1 pixel. And here they are showing few different examples. The teapot example I already showed you, but here you can see a cup example where cup with this single black dot, which may look like a food particle dust or something to you. If that circle was not there, it is modified, and now the new prediction is soup bowl. And here a bassinet is classified as paper towel, and here a hamster, which was the original prediction, because of this one small black dot added, it's being predicted as a nipple. It's so interesting, it's so funny, and this is so amazing to learn more about the vulnerability of neural networks. So the theoretical idea behind one pixel attack is the following. Let's say I have a neural network which can predict an image which has n number of pixels, right? So F is the image classifier, which is the neural network, this F, right? And I have an image with n pixels. Now, this image with n pixels we can represent as a vector having n dimensions, right? Each pixel forms one dimension. Then what we mean is if X is the input image, which is the original image, consisting of n dimensions, x1, x2, x3, etc. up to xn, where x1, x2, etc. are the values of the individual pixels. And let's say the target image classifier F classify this input image X into a class T, right? Then we can define the probability for X to belong in the class T as Ft of X. So Ft, this T is actually supposed to be underscore. So F underscore T, F subscript T of X. So F subscript T means the function F, which is the image classifier neural network, is classifying this input image X into class T, and the probability for that is F subscript T of X. Usually, in calculating adversarial perturbation, what we do is we add another image, right? The noise image which you saw, the number of pixels in the noise image was exactly same as the number of pixels in the input image. So this is how the regular adversarial attack works, not the one pixel attack. So just ignore the title here. So basically, the perturbation can be represented as E of X. Why is it E of X? Because it depends on the input image X, and that we can represent as E1, E2, etc. up to En. So the perturbation vector, which is added to the input vector, also has n dimensions. And the target class, let's say, is adv. I'm just putting it in italics. This is the target class. So initially, the neural network was classifying the original image X as class T, but now the perturbed image, which is X plus E, will be classified instead of T. It will be classified as adv. Okay, and we do have a limitation. The limitation is the magnitude of the perturbation that we add has to be limited. We cannot add a huge magnitude because then the change in the image will become perceivable to humans. So we limit the maximum modification L that we bring to any of these pixel dimension values. And basically L is measured by the magnitude of vector E of X, magnitude / length of the vector E of X, where E of X is the added perturbation. But so we can mathematically represent this, right? So we are trying to maximize the perturbation such that the target class, instead of T, it is add with the class. F is the original neural network. And what is the input image such that instead of T, the predicted class is add, it is X plus E of X. Okay. And what is the constraint that we have? The constraint is that the magnitude of the perturbation should be limited. And this limit L is defined by, carefully seeing what is the perceivable change for an image that we can kind of tolerate. Okay. In one pixel image, we are essentially doing something very similar, but we have another type of constraint. So we are trying to make the neural network F make a prediction into class adv instead of class T. We are modifying the image X by adding a perturbation E of X. So it is X plus E of X. But instead of saying that the magnitude of the vector E of X is less than or equal to L, we are saying the number of dimensions within E of X that we can change is limited to D. So in one pixel attack case, D equal to 1. What that means is the perturbation vector E of X can have only one of the values as non-zero. All other values, so it's an n-dimensional vector, all other n-1 values should be 0. That's the idea. And do we limit what is the value that we have to that non-zero element in the vector? No, we don't make any limitation. It can be as much as possible. This is the idea behind one pixel attack. The algorithm that is used to figure out which exact pixel to modify is called differential evolution. So this is the algorithm that is used in the paper. So differential evolution works in the following way. So we first select a subset of pixels, a group of pixels, as a set of pixels which may contain the pixel that we are finally interested in modifying. Then we create some mutation to these pixels. We define that there are, so each pixels are defined as vectors, and we make minor perturbations to these vectors, which are these pixel values. And we define that certain child pixels are created as a result of crossover between mutated pixels. And if these childs or these new generation pixels are satisfying certain condition, the condition could be how less confident are you, is the neural network now in predicting the true class? If has the confidence decreased or has it increased? So our aim is to reduce the confidence, let's say. then if the confidence has not reduced as a result of this new child pixel, we will discard it. We will try to again mutate the original parent pixels to create the next generation. So, and whenever the next generation of child pixels within the initial group of pixels that we select for differential evolution, if either of them are increasing the loss or reducing the confidence with which the true label is being predicted, then maybe we consider it as a satisfactory one. And then we do this again and again and again until we reach a threshold condition where, let's say, the loss is greater than this, or probability or confidence is less than 50%, something like that. So we encode the perturbation into an array, right? So perturbation, I'll show you in just one moment how visually this can look like. Then we evolve this using a technique called differential evolution. So the candidate solution, meaning, let's say one pixel is being changed. So pixel number 45 needs to be changed. Then we may select a group of 10 pixels as our initial generation of pixels. We will first perform slight mutation to the value of these pixels. And then we will we'll do a weighted sum of these pixels to create the next generation of pixels and see if the next generation is better or worse than the previous generation of pixels for increasing the loss or reducing the confidence of prediction. If it is better at making the confidence worse, then that new generation of pixels are selected. Otherwise, they are discarded. Then mutation is repeated, and this process is repeated until certain threshold condition of loss or threshold condition of confidence of prediction is arrived. And here, when they say each perturbation is a tuple holding 5 elements, x, y coordinates, and RGB value, what it means is if the pixel is a color pixel, it will have RGB, 3 values. It will also have 2 more values. The coordinate location of the pixel. Is it the 1, 1 pixel? Is it the 3, 5 pixel? Because you have a n by n image, let's say. So you have an array of pixels. So the pixel value alone is not what is important. The location of pixel is also important, because what we are trying to figure out is 2 things. Which pixel need to be modified in the 1 pixel attack, by how much it has to be modified. So that is why the RGB values and the XY coordinates both are important. And what we do is, in the perturbation, random perturbation, it modifies 1 pixel. Then let's say if the initial number of potential solutions, which are the subset pixels we assume as the first generation, if that is n, at each iteration, a new n candidates or new set of children are produced. If they are better, they are kept. Otherwise, they are discarded, right? This is the differential evolution. And visually, you can see before coming to this formula, I just want to show differential evolution visually. So here you can see how you will arrive at the target location, XY location of the pixel and the target value. So here you may initially start with random values between, let's say, 12 and 14, and you may pick these array of pixels ranging from, X location -4 to +4 or -5 to +5, and as a grid. Let's say you start as a uniform grid. You can start as anything, does not matter. And then you will slowly converge. So convergence is not guaranteed in differential evolution. That's an important point. Convergence is not guaranteed, but it's very likely that you will converge to a solution. And one interesting property about differential evolution is that there is one more way in which we can do the same thing, right? Which is gradient descent, which is what is done in neural networks. But the problem with gradient descent is that we need to be able to define the gradient of a function. It has to be differentiable. What if we have non-differentiable functions? So this evolutionary algorithm, like these meta-heuristic algorithms like differential evolution, it's applicable even in the case of non-continuous or non-differentiable functions. So it's very powerful. It may not be as efficient as gradient descent in terms of the speed with which it can find optima, but it is very powerful because it's applicable to many kind of functions. Now I'll go back to the previous slide just to show you the mathematical framework for calculating the next generation. So the generation g plus 1 is created as a function of the initial candidate solution. So let's say R1, R2, R3 are random number, and then xi is the new generation. So these are different xr1, xr2, xr3 are different candidates in the initial parent generation. Then we have a scale parameter, and here we are perturbing xr1 in generation G using xr2 and xr3, and kind of a scale parameter. We are using this parameter to perturb this to create a new generation called xi of generation G plus 1. Right? So G is the index of the current generation. Don't worry if you don't have a great mathematical intuition of how this works. Just understand that this is very similar to, not exactly same, but very similar to genetic algorithm. You are like making slight changes in the initial set of numbers, and you will discard the change if those changes are not fit for your goal. You will have a goal, right? Your goal is to maximize the loss or reduce the confidence. So if the new generation is not fit towards accomplishing your goal, you will discard that. Otherwise, you will accept it. So it's kind of like survival of the fittest in actual evolution, biological evolution, right? So that is the idea behind differential evolution. And the data set that we will be looking at today when implementing the one pixel attack for a particular neural network called ResNet will be CIFAR 10 dataset. So it has 10 classes: airplane, automobile, bird, cat, deer, dog, frog, horse, ship, and truck. And this has 60,000 images, 50K for training, 10K for testing. These images are 32 by 32 pixel. So although in this grid of sample images, you can see that the images look good, when you zoom in, it may not look as good because there are only like 32 by 32 pixels in each image. So it's not like a very high resolution image. But because of that, this works really well when we are implementing one pixel attack. When the resolution of these images are very high, if there are like 1,000,000 pixels, if it's 1,000 by 1,000 resolution image, then there are like 1,000,000 pixels, right? And if it's like 1,000,000 dimension vector, just changing one of the dimensions of this vector is likely not going to change the target, which is the prediction made by the neural network. So that is one reason why we deliberately select this CIFAR dataset. All right. So now what we will do is we will move on to Google Colab and we will implement the one pixel attack in code. I will also share the link to the Google Colab notebook, and I'll also show you the original GitHub repository in which this code was published. But I have made a few modifications because there were certain packages which had become obsolete. There were several other modifications that I had to make. So I myself have hosted this code base in my own GitHub repository, which I'll be sharing as well. So let's move on to the coding. This is the original one pixel attack GitHub repository. It has a huge number of stars. And what they do is they take a few different neural networks, including ResNet, and they calculate. So this code base is what is the base of the one pixel attack paper. But we don't want to do such an extensive job. We just want to implement it for a few images and see for ourselves how this works and get confidence that we can also implement one pixel attack, right, in practice. That's what we want to do. So I have forked this repository and made a few changes. And I'll tell you what all changes I made. So firstly, I forked this and I took the repository to my remote, like to my personal computer. And then I hosted it on, I uploaded it to Google Drive so that some changes that I make are permanent. So I am actually connecting, let me actually do this. Clear outputs, and I'll just disconnect and delete runtime so that I can start everything from scratch so that you can also see from the step number 1 how this looks like. So what I've done is into my Google Drive, I've uploaded this by creating a folder named one pixel attack. So in this folder is where I have put all this content. Okay. So here we'll be only needing a few Python files. So first this IPyNB we'll need. This is the one pixel attack code. So using this, I have created my own version of that, which is this. So we'll be needing this particular, what you see now, this one pixel attack.ipy notebook in Colab. We will also need helpers, this helper.py. This file, we will need differential evolution.py. This helper has several plotting and file formatting modules. Then differential evolution is the algorithm for the kind of the genetic evolution of the initial set of pixels to arrive at the right pixel and the right pixel modification. And inside networks, there is another code called resnet.py, which is where a modified residual neural network is defined. It's a small ResNet. It's not like ResNet 50, or it's not like a big neural network. So we will need that also. So in my local code base, I have put the ResNet. I copied the ResNet and pasted it here. Here meaning into that outside folder. So I'll show you that in a moment. So first, let's do this. First, we will mount the Google Drive. So this is the process that connects the Google Drive to the Colab. And it will show you a pop-up asking your permission to make this connection between Google Drive and Colab. And then, of course, you can grant the permission. We'll show you that in a moment. Yeah, so connect to Google Drive and just select your account. You must be already signed in for this, otherwise you'll have to type your password. And then now the Google Colab and this Google Drive are connected. Next is I will define my working directory. So I think here, if I just run the working directory by running present pwd present working directory, I guess it will show something else. Let's see. Mounted at this thing, and present working directory should be it's slash content. But I want my present working directory to be this. Slash content slash drive slash my drive and slash 1pixel attack. So you will see that here you click this, go to drive and my drive, and there you will see 1pixel attack if you open this. So that is where the directory is. And I am changing my path to there. So just run this part and then it can print the current working directory. So now the current working directory is this. Okay. Once this is done, we can import a few packages, import pickle, numpy, pandas for manipulating the tabular data, matplotlib for plotting figures, CIFAR10 dataset. This is the one which we were using, the 32 by 32 pixel images with 10 classes, keras for dealing with neural networks. So we'll import this, and I don't believe this system.path.append is needed, because I think our path is defined as this. So you can even I would say comment this line. Next, what we are doing is we are importing ResNet. So you might wonder, where is this import happening from, right? This is not happening from the internet. This is happening from here. So in OneDrive, there is a 1pixel attack folder, which is over here. This one, right? So in this 1pixel attack folder, there is a ResNet. You see this one. So this resnet.py is this ResNet. And we are importing the ResNet from inside this resnet.py, right? So this is not from internet. And this is happening because we have defined the system path to be slash content slash drive, this one, right? So let us import ResNet. And after importing ResNet, we will be, let me just close this. We'll be importing the training dataset and testing dataset. So that is loaded from CIFAR10. So let's run this. This is quite fast. Dataset is not at all very big. And these are the class names, actually, the 10 class name, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's a 10 class classification. Okay. So we'll just run this so that the class names variable is defined. And now this import helper is also from this folder, which I showed you. So this is the folder, helper. Within the folder, this helper.py is what we are using, right? And then we will select a random image of image index 99, and then we can just plot it to see how the image looks like. It's that of a horse. Or if we select some other image, let's say 31, it will be some other image in one of these 10 categories. This is dog or something. So let me go back to the original image. It was 90 something, right? 99. Yeah, this image, right? This is the horse image. Now we define an image perturbation function, perturb image function, in which we modify one of the pixels. Okay. So we select the same horse image, image with index 99 as the sample image for perturbation. And we will just define an array of 5 values. You might already be able to guess what are these 5 values. The first 2 values are x, y coordinates of which pixel. We are modifying 16th index 16th index along X dimension and 16th index along Y dimension. That pixel we are modifying. So I think it might be somewhere around here and here. So in the middle, right here in the middle, I think, because this is a 32 by 32. So 16th might be somewhere here in the middle. Y dimension is also 16. So I think one of these pixels is being modified. We'll see that in the next step. And how much are we modifying it to? We will modify it such that red plus green. So there is a red value 255, green value 255. So I think what is red plus green? Red plus green result. I don't know what is this. Yellow. Okay. My art skills are not good. But anyways, so hopefully what should happen after we run this is into the image perturb, we pass the image the X test of image, which means this is actual image itself. We also pass the pixel which we want to modify, and then we will plot the perturbed image, which should hopefully look like this pixel of one of these pixels of the horse looking yellow color. Let's see if that is happening by running this piece of code. Yeah, so one of those one of the pixels in the middle became yellow color. Now you might be able to guess if this was 255, what would happen? R plus G plus B. Red plus green plus blue is what? White color, right? So this will become white instead of yellow, right? If this was 255, 0, 0, if it was like this will become what? Red. And if instead of 16, 16, if it was, let's say 0, 0, then it would be the very first pixel over here. That is the one that will get changed, I think. Yeah. And if it was 33 by 33, what would happen? It will be undefined because this thing has only dimensions up to 32 pixels. See, this does not work. So if it is 31, I don't know if the index starts with 1 or 0. So let me try with 32. Maybe this also will not work. I think index starts with 0, right? Yeah. So if it is 31 by 31, it will be the last last pixel. See, this is how the perturbation works. Okay, but this is a sample perturbation. We have no idea which pixel we have to perturbate, by how much we have to perturbate. These two things we are yet to figure out. So first, let us define our model function, which is the ResNet itself. So we will put that into this model's one-dimensional array. So we have loaded it, and next we will just print some statistics of this residual neural network. So statistics meaning basically the classification accuracy. There are 50,000 training images and 10,000 test images in the original CIFAR dataset. So we will just see how accurate is this ResNet on that dataset. I assume the accuracy will be very high, but either way, this is not going to take too much time. So the performance is as follows. We have the ResNet model, accuracy is 92%. Now what we will do is we'll try to make some predictions using this ResNet on certain images. Okay, so we are predicting the class of certain image that we will select. So image ID is 384, and we are modifying the 16th pixel, 16th, 13th pixel by this much, 25, 48, 156. Okay, so now we can see what's happening. So initially okay, let me do this. Let me not print. I'll come to that. So model is ResNet. True class is this one. So we can print true class of this particular image. I will comment all of this. Let's run this. Then it should be bird, I guess, right? Okay, 2. True class is 2. 2 is what? 0, 1, 2. We had all the classes here. 0, 1, 2. I'll just copy paste this class names here. So for our reference. So these are the class names. So if true class is 2, what that means is I can also print class names of true class. This should print bird, hopefully. Yeah. So the true class is bird. Okay. And now we can print prior confidence. So this is basically printing the confidence with which this is saying it's a bird. So print prior confidence. So it's bird with a confidence of 70%. Okay. So now what we will do is we are modifying the image. So we are modifying it using this which one? There is model.predict classes, this predict classes function, in which we are perturbing the image using the perturb image function, to which the XY coordinates of the pixel to be modified and the value by which it has to be modified and the input image are provided. And then on top of this perturbed image, we are calling model.predict. Here we are calling model.predict on the original image. So now we can print the new confidence, which is confidence after modifying the image. We'll also see how the modified image looks like. Okay, that also we'll see. So the new confidence of new prediction is 0.0001, which is 0.01 percentage. So for whatever reason, magically, when we modified the image using these pixel, when we modified these two pixel, this pixel 16,13, that pixel, if we modify by this value of RGB, then the prediction confidence will go drastically down from 70% to 0.01%. So we can also plot the perturbed image as well as the original image. So actually, we can just plot the perturbed image. You can see how which pixel was changed. So if this pixel is changed, so the original image was this. It is X test of image ID. It is simply X test of image ID. Let me just show that. Right, so we'll plot the original image as well as perturbed image. So original image look like this. Perturbed image is this. What's the error? Helper plot non-type object is not okay. Whatever. It's plotting, so I don't care what's the error. But anyways, let me delete that. So now you can see that when we modify this pixel, confidence is reducing drastically. Will the same thing happen if we modify some other pixel by some other amount, or the same pixel by some other amount? Let's see. I mean, I can just make this 0, this also 0, and see what's happening. Maybe the confidence does not reduce. Maybe it will increase. Who knows? Here also it reduced. You see, what if I modify this pixel number 1,1? Does the confidence reduce that much? Maybe not. See, it did not reduce that much. From 70, it reduced to only 68.5%. Maybe it will also increase when I randomly pick some other pixel, 10,1. How about this? See, more confidence increased. So when I change the value of this pixel from what it was originally to this RGB, so let's keep this one thing. Let me keep it 000. So basically, what I'm doing is I'm converting this pixel into completely black. Okay, and we can see that the confidence is increasing. Like this is a bird. Yes, this is a bird. And all I did this, I changed the value of this pixel into completely black from, I think it was green originally. But if I don't do that, if instead I change my original, I think it was this, right? Yeah, I think it was this. If I change this, the confidence will go from 70% to 0.01%. So the goal is identifying how did we know that this pixel is the one that we have to modify, and how did we know that this is the value by which RGB has to modify? That is the differential evolution, how we will figure it out. Okay, but I hope you now can see in front of you the degree by which confidence is reducing. If you randomly select this, if you select 1,13, this may not happen. See, confidence is not reducing that much. If you select 1,31, again, confidence may, instead of decreasing, it may increase. So there are specific pixels which really contribute towards classification accuracy, and if those pixels are messed up, that's when you really have a wrong classification. That's what our goal is. And we can also define like a attack success. I'll come to that in a moment. So let me do one more thing. Let's see prior confidence and attack success. Okay, success is just true or false, right? So here we will define success as something like this. If predicted, so okay, let's go one by one. So image ID is 541. It is this man sitting on top of a horse, and we are changing the 17,18 pixel, which might be somewhere. Yeah, it's literally this pink pixel, and the modified value is 185, 36, 215. If this was 0, 0, and 0, this will be black. Okay, and the true class is, we can print the true class. Print class names of true class. Yeah, the AI Gemini already had class names of true class. we can see what is the true class. It must be horse or something. Yeah, so it is horse. This is the true class. Okay. Now, what we did is we modified the image, this pixel in particular, pixel number 17, 18 by this much. And using the modified image, we now have a reduced confidence. I was the earlier confidence was 0.5. The new confidence is 0.07. Let me just attack success confidence. Prior confidence, new confidence. Let me call it as new confidence so that I'm not getting confused. So new confidence is 0.07. Prior confidence was 0.5. And what do we define as the success? We define as the following as the success. So attack success, right? So we are defining it as true or false. So we have new confidence is this, and old confidence is this. And if the predicted confidence is such that you cannot anymore say that I have more than 50% confidence that this is the predicted class, then you will say attack is success. So one more thing you can do here is you can print the predicted class. So print predicted class of class name. Class names of predicted class. We can print this to see what class is the new image being predicted as, the new modified image. I hope we can see that here. Okay, so okay, I think we have to print class name, new confidence. So you see, this is predicted as a cat. So new prediction. The new prediction is as a cat. You see, old prediction was that of a horse. New prediction after we modify is that of a cat. So basically what we are saying is if this pixel is changed to this pink color, basically the neural network, instead of seeing a horse with 50% confidence, it will say now it will see a cat. So this 0.07 is now the new confidence of the previous class. So it does not have any confidence that this is a horse anymore. Okay. It's amazing. I mean, you can bring it to any class. We can play with this. Let's say instead of changing, let me take another image, right? So let's say image number 1. How about this? What is this image? New prediction is ship. Old prediction is also ship. So it has very high confidence. So maybe I can. It's very hard to, I think, by trial and error come up with. I think it's very hard to come up with trial and error which pixel to modify. So I will not attempt that. But here you see what's happening. This is exactly what one pixel attack is. We attacked this one pixel. Original prediction was horse. Now it is cat. It's as simple as that. Okay, now let us run this piece of code, which will basically help us do the attack via. I think we are calling the differential evolution somewhere. I'll just show you. Yeah. So here we will define the differential evolution. We'll come back to this attack part. Okay. So here you will see what's happening in a moment. So here basically what we are trying is we will show you through differential evolution how to identify which pixel to change and by how much it has to change, so that from the old prediction of, let's say here in this case, it was something else, frog or whatever, it is flipping the prediction. It's making the prediction something else. We will see how to do that. Yeah. So you see what happened. So it ran a few iterations. In all of those iterations, new prediction, even after modifying the pixels by something, random modification in the differential evolution. So this differential evolution is being called somewhere. Yeah. See here, differential evolution is called. And it was frog, 84%, frog, 3.3%. The moment it becomes less than 50%, I think, confident frog, there is a dog with 0.46 confidence. So now confidence of being frog is completely gone. All we did was change the value of this pixel. So we changed the value of this pixel through differential evolution, which we discussed before. And the degree by which we have to change this pixel was also identified through differential evolution. And suddenly this image, which was being classified with 84% confidence as frog, is now being classified as dog. It's amazing, right? Now we will see a few more examples like this. we can actually play with this. So instead of this image ID, what if I just run this image ID 19? I don't think this will, by the way, work always. Okay, this may or may not work depending on the pixel. So here image ID 19 is being classified as frog with 99.9% confidence. Is that actually a frog? Let me just print image ID 19. Let me, this looks like here it won't work. Like here the differential evolution won't work because the prediction confidence is so high. So this is image ID 19. So I'll put 19 here. I don't want to perturb the image, so I'll just call this function just like that. And let me end this code. I don't want to run it any further. I don't think differential evolution will work in this case, but I just want to see if 19 is actually frog or not. Yeah, okay, it is a frog. All right, so do I need this 0? I don't know. Let me see. Yeah, I don't need that. So this is indeed a frog, but what about something else? What about 191, random image? What is 191? Okay, I think we'll have to finish running that to see what is 191. It's a ship with very high confidence. So whenever confidence level is so high, maybe it's difficult to identify a new class through differential evolution. Depends on the kind of the image. So not all images can be classified into some other target class. Okay, so that is difficult. So that is why we'll have to do a little bit of trial and error, which I'm okay doing here. What if I take image number 30? I just want to find an image where the prediction confidence is a little bit low. Then we can see, okay, this is 93. Maybe here it will work. Maybe, I'm not sure. 93% confidence looks like it's not decreasing at all. Maybe then I will, okay, it was decreasing. Okay, let me run this once again. Maybe it will decrease. It will become, from a frog, it will become some other class within the remaining 9 classes. We'll see. So I'm pretty sure when we print this will look like a frog. Okay, it is a frog, and now it became a cat. You see? So here, did you observe one thing? It did not take that many iterations actually. So differential evolution is random mutation and non-random selection, right? That's basically human, like, or in general, organisms evolved by random mutation and non-random selection. Here also the mutations are random, but the selection is non-random. Why? Because selection is based on a criteria. What is the criteria? Whether the predicted confidence is reducing or not, right? So here, essentially this image, which is a frog with 96% confidence, will become a cat if we just change the value of this 1 pixel. It's beautiful, right? You will think, how is neural network saying that this image is a cat? Why? Does it make any sense? It looks exactly the same. No pixels have been changed. So 32 multiplied by 32 is what? It's 1024. So there are 1024 pixels in this image. Just one out of those 1024 images, pixels is changed. Remaining 1023 pixels are the same. And this is what you have. So it's, oh, is it actually 32 by 32 is 1024? Yeah. So this is fascinating, right? So imagine you have a 1024 dimension vector. You change only one of the dimensions of your vector, and suddenly the vector is being classified into something else. That's what's happening. It's so mind blowing. It's so I mean, the concept is very simple. I get it, but it's still mind blowing. So I will share this code base with you. I'll share the GitHub repository with you. I highly recommend you to try this. If something is not working, just let me know. I'll be more than happy to help. And we'll be covering more such concepts related to adversarial attacks, generative adversarial networks, etc. in the upcoming lectures. Thank you so much, and we'll see again in the next lecture. Until then, bye.